This is a photographer's shot of the Milky Way. So, would you believe me if I told you that each of those stars, each of those heavenly bodies up there obey certain laws? In fact, everything else in this earth obeys these formulas, among many other formulas. So, some of those formulas you may have encountered before, some maybe not yet. But these are just a small part of the many physics equations that govern everything we see every day around our environment and in the universe. So each of those planets, each of those stars and galaxies are exerting gravitational forces on each other. So the equation we see here above, it shows the gravitational force between masses, certain masses separated by certain distances. Indeed, there is an attractive force between any and every two objects. Isaac Newton did not discover gravity, but he discovered that gravity is universal. So the legend goes that he was sitting under an apple tree when an apple fell from the tree and hit him on his head. One thing led to another, but he realized that if gravity acted on an apple that is high on a tree, then why should it not also apply force of attraction to objects like the moon, objects like the stars even? He was later able to prove that everything acts on another object with a gravitational force. And that's why we call it the Newton's law of universal gravitation. In this formula, we use T, but sometimes R is used. So let's look at this example. This time, the capital M is used for mass, but it means the same thing. So we see that, or there are two arrows that have equal magnitudes. Each mass is attracting the other mass. So in other words, there is mutual attraction. This follows Newton's third law of interaction, where we have action-reaction pairs. Let's look at how masses interact and how the gravitational force changes as you change the various parameters. By default, using the original formula, if we simply have here, as we can see above in this example, if we have two masses and they are separated by a distance. By the way, when we talk about distance, we're talking about the distance of centers of mass, or the distance of the center of this mass to the center of the other mass. So we're talking about the center of masses, and we consider the objects, no matter the size, no matter the volume, we consider them as point masses. So for this configuration above, gravitational force is given by F. Now, for the one below it, what would happen if the mass of the other mass is doubled? So it becomes 2m rather than just m. What happens to the force? So it actually doubles as well. So we have twice the force, because the force of gravity between two objects is proportional to the mass of each one, and also the product of the masses. If we now have twice the mass for both masses, then what happens to the force? It becomes 4 times the original. What about if for the one below, if the mass is now 3 times the original? We have 3f. The effect of mass on the force of gravity is very easily predicted. But now let's look at the effect of distance on the force of gravity. So looking at this one, if we double the distance, the gravitational force should weaken. But does it become 1/2 or something else? So it actually becomes 1/4. the original. That might not be expected, but if we look at the next example then, if we bring the two objects closer together so that their distance becomes half of the original, what happens to the force? Does it double? No, it quadruples. So there's actually a different interaction compared to the effect of mass on gravity. So now, what if we double the masses of both objects and we also double the distance? So what will happen to the force? The force should quadruple because of the changes in the mass, but now the distance is also doubled, so it becomes 1/4. We are left with the original force, gravitational force of attraction. So the thing that we noticed about the effect of distance on gravity, gravitational force, we saw that there is a square term, or there is a squaring effect. And in fact, a lot of things in physics obeys that what we call inverse square law. It is obeyed by light intensity. Maybe you noticed that as you go farther away from a light source, the intensity drops. And this dropping of intensity actually follows the inverse square law. It's not linear, but it follows an inverse square. This is also true for radioactivity, the magnetic field strength, electric force, and sound. If you increase the distance, it's not a linear effect on the gravitational force. In fact, if you look at a graph, that's how the drop-off looks. Pretty much, it escalates quickly as you go farther and farther. You would be surprised at the amount of dropping of the gravitational force that you can find. So if we were to extrapolate this in a thought experiment, does the Earth still exert a force on you when you are at the other edge of our galaxy, the Milky Way? So the answer is yes, because there is still a finite distance of the Earth from us, even if we are at the other edge of our galaxy, even if that's 100 or a few light years across or away, there's still a given distance. So you can still have a value of F, force of gravity, that is non-zero. Can you ever be free of all gravity? So in Over the Moon, Fei Fei sang, "I'll be free of all gravity." So is that even really possible? Can you be free of all gravity? So you cannot, because there's always a mass close to you, whether it's the Earth, whether it's the sun, whether it's just the laptop in front of you. There is a gravitational force between any and every object with mass. So you can never be free of all gravity, and you can never be free of the Earth's gravity as well, no matter how far you are away. So there's always a non-zero gravitational pull, even if you cannot feel it. Now we will talk about the value of G, the value of big G. Although Newton already knew that the force of gravity is very weak, and therefore the big G, which he established as a placeholder, would have a very small value, he was not able to determine it himself. All he knew was that big G was very small. So it was approximately 100 years later when Henry Cavendish was able to measure G to be equal to 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. What's with the weird unit? This unit is just so that the other units in the formula of Newton's law for universal gravitation, the meter squared and the kilogram squared, would cancel out, leaving only newtons as the unit, which is the unit for force. As you can see, the value is times 10 to the negative 11, which is a very, very small number. And this is a testament to how small, how weak gravitational force really is. You need a super large mass, like the mass of the Earth, just in order to feel the gravitational force. Here is one version of how Cavendish measured the value of G. If you follow the cursor, there are two masses, one smaller and one larger. There is a known distance to their centers of mass, and you have a force on the other side of the balance, such that if you move big mass m, big M, right underneath small mass m, then the gravitational force of mass would attract the smaller mass m, and therefore you would have to rebalance the scale by adding more masses to the big F you can see here. So I will show you a video showing that. You will not be able to hear the narration. So what you see here is actually what we call a torsion balance, where there are two masses on the ends of a rod. And what you will observe is that if you add two large masses on either side of the circle, the combined effect of these two masses is that there would be an attraction of the two smaller masses. So those aren't magnetic, by the way. The attraction is purely because of gravitational attraction. So 152.166 grams, the mass of the small pyramid. We place a large mass right underneath. Then it becomes 0.167. So there's a 0.001 difference in the mass, but that is not actually a change in mass, but just a greater gravitational force of attraction due to the effect of the mass, large mass, which is very close to the pyramid, plus the effect of the Earth's gravitational force. The formal formula is actually the one you see at the top. It's big G times the mass, the two masses, divided by the square of the distances between the center of masses. The one you see here right now is actually the special case for when we have the mass as the Earth. I mean, when we're talking about the Earth and an object M. So the subscript E pertains to Earth, and here we have the values for the exact value for G, or it's not actually exact, it's still rounded off to 4 significant figures, and also the exact value for the mean radius of the Earth, which is 6,371 kilometers, and the mass of the Earth is 5.972 times 10 to the 24 kilograms, which is a very, very large number. We have a value small g here below. We have a formula, it's identical to the formula above, except for the missing small m. And we will talk about that a little later. Let's have some brain exercises first. While wearing the same clothes, do you think you would weigh more or less when you're on top of a mountain compared to when you're on the beach? You should be able to explain your answer. Number 2, how much would a 400 Newton person weigh when she or he is 1 Earth radius above the surface? So rather than being on the Earth's surface, you add 1 Earth radius above. So what would happen to the weight of that person? And number 3, how much would a real-life Physics 1 teacher who has a mass of 59 kilograms weigh if the Earth doubled in mass and nothing else changed? So you can pause the video and I will tell the answers right now. If you are wearing the same clothes, you would actually weigh less, but only slightly less, because as you go farther from the Earth's center, if you are at a greater altitude, like in a mountain, that means greater distance from the Earth's center, greater value of D. So we know from the formula and from the exercises we had earlier that this would mean a reduction in the gravitational force. But actually, that decreased weight is actually a very small difference. So let's compute the weight difference if the mountain were 1,500 meters tall. Like if you were on a mountain in the Cordilleras, particularly here, Baguio City is around 1,500 meters above sea level. Here, you would compute the acceleration of gravity to be 9.8057 meters per second squared. And therefore, if you multiply that with the mass of someone like someone who has a mass of 59 kilograms, that would only result to a 26-gram reduction. Okay, so it's not even measurable by a typical weighing scale. So there's only a 0.044% difference in the gravitational force. Okay, a very, very small amount. Now, how much would a 400 Newton person weigh when she or he is 1 Earth radius above the surface? So that person would only weigh 100 newtons. How? First, you convert 400 newtons to mass. You can use the 6371 kilometer radius of the Earth as the distance, and you just need to multiply the Earth radius by 2 because the person is already 2 Earth radii away from the center of the Earth. Now for number 3, how much would a hypothetical Physics 1 teacher, or actually this is a real physics teacher, weigh if the Earth doubled in mass and nothing else changes? So the main effect of this is actually just twice the original weight. So you need to multiply it by the acceleration due to gravity, 9.81 meters per second squared. You would have 1,200 newtons. Although we know the value of G to be 9.81 meters per second squared, it's actually not that constant. It varies from place to place due to altitude, for one, because as you go farther from the center of the Earth, you would expect it to be lesser. And the local geology, because there may be massive deposits of heavy metals or other things below the surface, and the overall shape of the Earth, which is an oblate spheroid. You would expect the countries near the equator or at the equator to have lesser acceleration due to gravity. As you can see in the equator here in the table, there's 9.780 meters per second squared compared to the North Pole, which is calculated to be 9.832 meters per second squared. So we will now talk about the gravitational field and the gravitational field strength. The person, this yellow person standing here, is experiencing a uniform gravitational field. What is a gravitational field? You can think of it as like an aura or something that is present everywhere around any object that has mass, and it has the potential to attract any other mass that is placed around it. By attract, we don't mean that it will necessarily actually cause motion, because there can still be attraction even if this force of attraction is so weak that it doesn't cause any acceleration. What we will observe in the figure of the globe, there are red areas, yellow areas. These hotspots show where the gravitational field strength is greater. So you'd expect the value of G to be higher in those places due to the local geology. Now, what do these lines mean? We can observe that they are equidistant. Okay, they are placed in equal distances, and they are uniform. They are all directed towards the downward direction. This means that the gravitational field at the surface of the Earth is uniform and it's constant, and it has a value of 9.81 newtons per kilogram. So how did it become newtons per kilogram? As we can see in the formula above, this one. So the gravitational force divided by the mass will give you the gravitational field strength. This is also equal to the formula that I introduced earlier. It's equal to big G times the mass of the Earth over the radius of the Earth squared. I mentioned that the direction is downward, but actually it's towards the center of the Earth. If you would look at the Earth from point of view outside the Earth, you would see that these lines, field lines, are radial, and they point directly, or they point towards the center of mass. So by definition, a gravitational field is a region in which a mass experiences a force due to gravitational attraction. When we see that the lines are closer together, that means the gravitational field strength is greater. And if they are farther apart, as we can see as you go farther away from the Earth or from the object that is causing the gravitational attraction, we can see that the attraction becomes lesser. So this is actually similar to the electric fields and magnetic fields, which you will talk about when you tackle the electromagnetic properties, perhaps in physics 2. Now, as you remember from Earth science, the Earth is a giant magnet. We can see that the field lines, which are imaginary, by the way, they aren't physical lines. So these are just visual constructs for us to be able to analyze these phenomena better. So these field lines are closer together at the poles because that's where the magnetic field is greatest. Now for these two examples, these are electric charges, and for a charge that has a lesser magnitude, it will have a weaker field compared to that of one with a stronger or higher charge. And we show this visualization by making the field lines closer together and by adding field lines. In gravitational fields, they can only be attractive. This is a screenshot from one of my favorite YouTuber, Flippin' Physics. Here, where he talks about gravitational field, we can see that the value of G, which is the gravitational force divided by the mass, it actually has a constant value of 9.8 meters per second squared, or 9.8 newtons per kilogram. So even if the mass changes, for example here, we have a blue umbrella which is roughly 1.06 newtons, a blue ball which is 26.4 newtons, and this physics book which is 37.1 newtons. If you divide these by the masses in kilograms, you would get the same 9.8 meters per second squared all throughout. So in essence, gravitational field, or the gravitational field strength, which is given by G, is equal to the gravitational acceleration, and by concept, it's just a uniform way of looking at the force that gravity can exert on an object with a certain mass if it is brought at a certain distance to that massive object, for example, the Earth. Every object actually has its own gravitational field, but not all objects can attract other objects physically because this gravitational force is usually negligible or very small compared to the gravitational force that the Earth exerts on every other object. But it still follows the Newton's second law, where we add up all the forces in order to come up with a net force, and this net force will govern what would happen or how the object would behave. So here you see a picture of me with my daughter when we were in the International Space Station and we experienced weightlessness. As you can see, everything is floating and we were really having fun. If you recall our elevator thought experiments, a person who is standing in an elevator would feel weightlessness if the cable of the elevator were to snap, and that is just apparent weightlessness because the person would still have weight, but since she is standing on a weighing scale that measures the normal force, then there would be no normal force, and therefore the apparent weight of that person would be 0. So there is apparent weightlessness. But is there really true weightlessness? This would mean that the gravitational force is 0. So is that possible? It can only be possible if the mass of the Earth would become 0. And we wouldn't live to talk about it if that's the case. For our last example, the ISS, International Space Station, which is 420 metric tons, is orbiting around the Earth at an altitude of 429 kilometers. What is its weight at this altitude in relation to its weight on the surface of the Earth? You can pause this video now, and I will tell the answer later. So, if you tried to solve it, here's the answer. Let's see if you're right. So first, you can compute the weight at the surface of the Earth by multiplying 420 tons to 9.8 meters per second squared. But you need to convert 420 tons to kilograms, so you just multiply that by 1,000. Now, for 429 kilometers, you need to add this to the 6371 kilometer radius of the Earth, and then you have to square the whole thing before doing the math. You will compute an answer of 3.62 times 10 to the 6 newtons, which is just 88% of the original, or of the weight on the surface of the Earth. So this is a real physical reduction in the weight of the object. And you can work out that G, or the acceleration due to gravity, or the gravitational field strength, is only 8.6 meters per second squared at this altitude. So what does that mean? It means that there is a reduction from 9.8 to 8.6, but it's still not 0. So there is still no true weightlessness, even if you are already floating up in the ISS above Earth's atmosphere. That's our lesson on Newton's law of universal gravitation. I hope you learned something, and feel free to leave a like. Till next time.